Everyone, welcome to the webinar on applications of formal verification. We'll be talking about history of formal verification and various aspects related to it. We'll start with why formal verification. Then we'll talk about history of formal verification. Then we'll go into transformation of formal verification. It started as a property checking to now what exists is the formal verification apps. And we'll also talk about how the formal verification is being used in the designs today, and looking forward, how is the formal verification going to evolve. So we'll talk all about this in today's session. We'll also talk about our workshops and also the webinars and boot camps which are coming up. I've sent a form link in the chat window. If you want certificates for this webinar, please fill that form and you'll receive your certificates on your email. So let's get started with this. So as everyone knows, verification is a big problem. There are a lot of time which is spent today's, and a lot of time of the project schedule is actually spent in verification. Around 50 to 60% of the project time in today's SOCs which are being built is spent in actually doing verification. And this trend is not changing. This trend is still going to be increasing. So this trend is increasing. So, and in addition to that, what is also happening is there is number of engineers who are working in verification is increasing. So they basically since 2007 for last 10-15 years, increase in verification engineers who are doing verification has been 146%. So there is a lot of demand for verification engineers. Still, people are not able to complete verification. So you can understand it's a growing opportunity and it's ever growing. And we'll also talk about how, in the context of formal verification, this fits in. So basically, what is also happening, and the trend which is very common, is even design engineers who are writing RTL spend around 50% of their time doing verification. So not only verification engineers are doing verification, in addition to that, design engineers, RTL engineers are also spending around 50% of time doing verification. So as an RTL engineer, also it is very, very important to know verification, how to write test benches, because not only verification engineers are going to do verification, even RTL design engineers are spending more than 50% of the time doing verification. So where as verification engineers spend usually their time? They spend their time in test planning, where you write test benches, where think about what are the tests you're going to do for a particular design you're doing, for a particular chip you're doing. That's basically a lot of time that is spent on that. Then the time is also spent on what is known as test bench development, then creating those tests, running simulations, running debug, and small percentages is spent in other areas. But you can see a lot of time is also spent also in test planning, because that is the base of doing verification. What you want to test is actually done in test planning. So in terms of doing verification, what are the various kind of techniques which are used? You basically check code coverage, you check functional coverage, you check assertions, you check constraint and verification. So all these type of verification aspects are used. One of the other aspect which we are covering today, we'll talk about what is the adoption of formal verification in the world today. We'll come to that a little bit later after we have talked about basics of formal verification. So basically, normal test bench or dynamic verification, what you do is you develop your test plan, you write your test benches, then you simulate and then debug, and then you cover whatever type of coverage you may be using, whether you'll be using functional coverage, code coverage, line coverage, or any other type of coverage, and you figure out how much of that you have covered. And if something is remaining, then you develop more test bench, and this cycle continues. So basically, you develop some test bench, simulate, then debug whatever is remaining, and then try to figure out with what coverage is remaining and develop new test benches for it. So it's highly iterative, as in some of the times you are able to reuse a lot of stuff which you have done previously, but you still are not sure what are the additional things you need to do to reach the coverage goal you want to reach. And this is the basically one of the major challenge of coverage closure. A lot of designs basically are able to reach coverage no matter how you are capturing the coverage to basically close to 100%, maybe 95%, maybe 96%, maybe 90, even 99%, but you're not able to reach 100% coverage. That's the limitation of this kind of verification, writing test benches, updating test benches. And also, you don't even, a lot of time, you don't even know how to hit the cases so that your coverage or your coverage goal can hit 100%. So basically, after a high percentage in 90, you reach a plateau. Okay. And basically, then after that, you're not able to increase your coverage further, or increasing the coverage very very slow to in relation to your chip goals or chip timelines. And that is what every verification engineer dreads, but it's part of life. It's what usually happens when you do dynamic verification, or the method we talked about, writing test benches and updating test benches to reach a certain closure. So what happens in a normal dynamic verification, or the verification you're doing using test benches or assertions, is initially you basically have a very high curve, high, and you are able to do very efficient verification. But as you start reaching close to 100% coverage mark, you start getting diminishing returns. What is the meaning of diminishing return? Is after initially, even with low effort, you are able to cover a lot of part of your design, but as you start reaching closer to 100% mark, 90% mark, the amount of effort required, or amount of work required to increase the percentage of coverage becomes very very low. You need actually low effort and with very low percentage coverage gains. And that's where basically this dreaded plateau comes in, where basically you start spending a lot of time and a lot of effort, and still not able to reach the goals, which is 100% coverage goals. And theoretically, in test bench based coverage, you can never reach 100% coverage goals. So this is where formal verification helps. But before we go into that detail, let's understand how typically a test bench or a dynamic simulation works. So you have a set of test suits, and you basically should think of this as a single case of that will be test bench, which you would have written in Verilog or similar languages. And basically you have a driver, you basically provide that, you check, run it, provide the inputs to what are the design under test dut, and you will have a reference either written in test bench or somewhere outside, where basically you know what is my going to be my predicted output. And then you will monitor the output which are generating by the design which you are testing, and then comparing on a scoreboard whether it's meeting your expectation or not meeting your expectation. And that is the normal flow of test bench or dynamic verification. Here what you are actually doing is you are giving some inputs, and let's say this is the space of whole of your design. Okay, so let's say design can go from this state to this state to this state, so multiple such possibilities exist. Each of the test bench that you are writing is executing this design in a particular state path, which basically you will provide some stimulus, it will move from this state to this state. You will provide some additional stimulus, it will move from this state to this state. So basically each of the test bench you are writing is executing the design to reach to take a particular path. So one test case or one test bench, let's say test one, will take this path in the design. And by what I mean by path is, let's say this is a state space. What are the states possibilities in the design? And so one test bench is gonna take this path. Other test bench is going to take this path. Other test bench is going to take this path. And as you can see, right, if it's a big design, there are multiple types of state possibilities with it. And It is theoretically, if not theoretically, probably practically very difficult to get all these state possibilities. So there are going to be some of these states which are going to be missed out, because going through each and every permutation and combination of states and possible permutation and combination stats gonna need a lot of thousands, even more than, like for an SSE, more than thousands of test benches. So this is where their functional simulation or dynamic simulation kind of falls behind or lacks or fails, because you need a lot of state space to be covered by writing a lot of test benches. So basically, now what formal verification does is, in formal verification, this is at very very high level. We'll go into more detail. Is you some kind, you in some way you're not writing any test bench for a particular path. You are giving what is known as something known as constraint to the design. Okay, this is what I want to. This is what you should assume, and we'll talk about how, what is the language of formal verification, how do you give that, what you should assume, and within that DUT will run, and how the tools or technologies which support formal verification will also talk about how those will run. But the very very different thing from academic simulation is, you're not writing test benches and you're not executing design for a particular state kind of path, which we were doing in test bench. So here you are executing the design on a particular state set of state paths, and let's say this is the whole state space. Formal verification, you're not doing that. So in formal verification, you are able to cover more without writing test benches and a lot of state spaces. Of course, that itself also comes with its own challenges, which we'll also talk about. But think of this is fundamentally different from writing a test bench where you're executing one particular state path in the state space. So this basically, you will give some inputs, but from a particular set of inputs, the formal verification technology or the formal verification tools can have multiple paths which are possible. So you gave one set of inputs, it will go on and verify multiple set of paths from the single set of inputs. Let's say you gave some inputs, all these states spaces from the single set of inputs will automatically be explored. So versus traditional dynamic verification, this gives advantage where one particular set test bench or one particular input was executing only one particular state path. But with formal verification, with one particular set of inputs, you are able to traverse or verify multiple possible state paths, and that gives you advantage that you are able to cover more and helps you to cover more, reach your coverage goal faster in some particular targeted areas. So the advantage is, we have not gone into details, but if you are able to consider, right, rather than writing one test bench and one test case for each state path, you are able to cover a lot more using this. So you get complete coverage, as in whatever you're testing, you get complete coverage of it. And you are able to do this with minimal test benches or example. So you, with a single maybe set of inputs, you are able to cover a lot more and complete coverage. And other advantage that it provides is, you are able to cover corner cases. So there can be some corner cases in the design which you may not have thought about and may not have written test bench about. But since formal verification provides complete coverage, it is able to also find those corner cases and verify those. So these are the multiple advantages you get because of running formal verification. So simulation, think of like trying to think of pictorially. Simulation, let's say this is whole kind of design space you want to cover. Simulation, maybe you are able to cover point by point. You covered this, you covered this, then you covered this, then you covered this, then you covered this. So point by point, you are able to cover spot coverage using simulation. Formal verification, theoretically, let's say ideally, if it works for all the cases, you are able to cover everything because you're not writing pointed test benches or pointed verification ideas. But in real life, formal verification does not demonstrate idealistic behavior. You are able to cover a large percentage, but maybe still some area you may not be able to cover. So it's practically it looks like this: you are able to cover a large shape of large area of design space, but may not be all. This is how practically it works. But you may be able to find full coverage in specific targeted areas, which we'll talk about as we move forward in this webinar. So why formal verification? What are the kind of advantages it provides? Is for dynamic verification, after initial effort, basically the ROI on writing more test benches, creating more testing becomes slow. Okay, and it takes a lot of effort and time to reach to 100% coverage. And typically, most of the design are not able to reach 100% coverage. I would say it will be very rare that designs are able to reach 100% coverage. Now, for that, formal verification comes into the picture. With one set of test bench or one set of inputs, you are able to cover a lot more. Okay, theoretically you should be able to cover everything, but practically for you, formal verification works good in only specific set of areas, and that's where formal verification adds value. So now let's go and understand what is the history of formal verification. How did it come to the picture? Some of you actually would have, who are working in design companies, would actually have used formal verification, and I'll talk about a particular application where actually you have used formal verification a lot of times. So let's first start with one of the interesting anecdotes about Pentium bug. Okay, so Pentium, as you know, is an Intel processor. It had a hardware bug. Okay, what was the hardware bug? Was the floating point. So it has a floating point divide. It returned incorrect answers in a very small set of cases, not everywhere, only very small set of cases. So it was a corner case bug. Intel, of course, right, as an Intel is a big company and it has been shipping out Pentium for a long time, of course, had a massive set of test suite, and still the bug slipped through. Okay, still there was a bug which was missed. And the cost of fixing this bug, or basically associated with replacement of flawed processor, was around 475 million. Okay, so this was the cost of incompleteness. And of course, this was 20 years ago. Today the cost of doing this will be, let's say for an iPhone, will be much higher. So you can understand, right, there is a big cost involved when you are not, when your verification is incomplete, because there can be corner cases which can be missed, and which is what happened on Intel Pentium. Basically there was a floating point divide bug which return incorrect numbers. And it's not that it can return incorrect numbers, like for example, it return incorrect numbers after a certain set of decimals. So it was really a very corner case bug. Still, it was very high cost bug for Intel. Okay. So after this, Intel decided, okay, to see how they can improve the verification coverage, because the cost of incompleteness of coverage was really high. So they thought, okay, let us see how we can actually increase our coverage and solve this particular problem. So in the aftermath of this bug, and of course they had to recall certain set of chips, there was increased basically usage of formal verification, at least for hardware of floating point operation and across the semiconductor industry. And basically it went then into improvements of tools and technology methodologies. Intel then went on to use formal verification very extensively later in the CPU architecture. And basically there were multiple verification strategies they had used, then tools and technologies were developed. Even Intel used it, the EDA vendors came out with a lot of tools and technologies to do formal verification, which we'll talk about as we go along. So this was the history of the formal verification. How did it come into the picture? It came into the picture, it's the same principle, that cost of coverage, incompleteness was very high. Now, what is the idea of formal verification? how it's able to provide a complete coverage. Okay, so here I'll go back to a school, typical school example, which is Pythagoras theorem, right? So for Pythagoras theorem, think of this, right? As in the Pythagoras theorem says a square plus b square is equal to c square, which where a, b, and c are the sides of the triangle. Okay, so a and b are perpendicular, and c is the hypotenuse of triangle. Now, think of when you're doing test bench based verification, what you are actually doing is you are writing, okay, if A is 1, B is 1, C is this, I have verified it. A is 1, B is 2, C is something which comes out, I have verified it. So basically, you're writing each and every kind of, uh, if you think of the analogy, you're kind of writing each and every value of A and B and then confirming it is matching this equation. And that is how a typical dynamic verification or test bench based verification run. So you're writing test bench for each of those cases. Think of that in the mathematical equation here. You're writing each value of A and B and putting into this equation and verifying whether this equation holds true or not. And as you can imagine, right, verifying this or checking this for each and every value of A and B is impossible, right? But if you are able to prove this mathematically, if you are able to prove by mathematical theorems or mathematical equations using some base identities, then you don't have to verify for each and every value of A and B. And that is the idea of formal verification, that if you can prove using, for example, whatever the mathematical methods are, you are able to prove A square plus B square equal to C square, then you don't have to verify that or test that for each and every value of A and B, because you have mathematically proven it that for all values of A and B, this will. And that is the idea of formal verification. Formal verification mathematically proves certain scenarios in your design that they will always hold true in your design. And that is why provides you complete coverage. So think of formal verification as mathematical proof or mathematical verification, and that you are able to prove for each and every value. Okay. So formal verification is the use of tools that mathematically analyze the design space or possible behaviors in the design rather than computing for particular set of values. So rather than computing for A equal to 1, B equal to 1, then A square plus B square equal to C square holds true or not, you are doing formal verification is doing mathematical analysis and proving that. And because of that, you will get 100% coverage or very high coverage without needing to write a lot of A is equal to 1, B is equal to 1, because you are proving this mathematically. So one of the very common application, which I'm sure as in if you're working in industry or maybe in your college, you would have used, is something known as formal equivalence checking. What happens is when you do RTL design, and after your RTL design, you do synthesis of that design. And when you do synthesis, a gate level netlist is produced. Whether the gate level netlist which is produced is equal to the RTL which was given to the tool is proved using something known as formal equivalence checking. And it's actually one of the aspects of formal verification. You are mathematically proving that, for example, whatever was the RTL functionality, the netlist does the same functionality. So what it does is for each it basically cuts the design into input ports, output ports, and the logic between flops. And what happens is the logic between flops or logic from input to flops or input to output is converted into Boolean equations. For example, in this case, the Boolean equation of F. So what basically F1 is directly connected to F2 through a buffer. So equation for deep in pin of F2. So equation for this logic is basically, let's say input is A, then the output is also A because it's a buffer. So the equation for this is, let's say, A or F1. Now, at the gate level, again, it will say, okay, whatever was the equation for this area is that equation here same or not, and prove that mathematically. Whatever the equation was here, is that math equation same here? Whatever was the equation here, is that equation same here? And prove that mathematically. So you'll find out what is the equation here, which is just a buffer. So basically, equation is f2 equal to f1. And here, what is the equation here? So equation here is this net is inverted of f3, and then it's inversion again. So f4 equal to f3. So the equation is same. So even though actual logic has changed, since the equation is same, you can mathematically, basically you can convert this to a Boolean equation and mathematically prove this function which is implemented here is same as this function. So this is one of the earliest, one of the very commonly used application of formal verification, which is equivalence checking. And typically, initially, people used to say, okay, you are doing formal verification means you are doing equivalence checking. But of course, the things have changed after that. This is one of the very common application of formal verification. So after that, what happened was a new language which was developed, system Verilog, which is assertions. As in, there were other languages also, but system Verilog assertions or system Verilog languages which has basically being deployed more. Here, basically, you write some assertions. Assertions is behavior of your design, okay, which is usually written in expressed in a language called system Verilog assertions. It's actually describing the properties of your RTL. For example, properties can be as simple, okay, when you apply reset, this flop goes to 0, or counter increases by 1 in every cycle. So basically, whatever are the behavior of your design, properties of your design, think of that in English, and they are converted into a language, which the most common used language is system Verilog. There used to be other languages as well earlier related to VHDL like PSL. Now, so those languages are used to describe the properties of your design. Now, but basically, just writing assertions is not complete for doing formal verification. There are tools and technologies which which basically are going to use those assertions to basically then do a formal verification on your design. So let's understand what that is the case. So basically, using these assertions, properties of your design are written. For example, when you put a reset, your design goes into reset. Or properties can be your counter increases in every clock cycle by 1. Okay, so basically, formal property verification is from the equivalence checking. It has evolved to where you write properties for your design, and those properties are written in something like system Verilog assertions, and then basically these assertions are mathematically proven by the tools in the design. People who join later, I have basically copied a form, link to the form. So who want certificate for this particular webinar, please fill that form and you'll get a certificate in your email. So let's continue. Okay. Now, one of the things which we said, right, as in there were challenges with doing simulation. Your verification was pointed verification. You will look into one particular aspect, write a test bench for it, and only do that verification. Ideally, if formal verification works correctly, or basically you are able to cover, ideally it should not have the problem like loss of coverage or only testing certain things. It should be able to cover everything. But in real life, formal verification also covers only specific targeted areas. And the reason for that is complexity in formal verification. When you're writing a test bench, for example, when you're writing a test bench, you are giving exact inputs: A is equal to 0, B is equal to 0, C is equal to 0, and those inputs are propagated in your design. But when you're doing formal verification, you're just writing some equation or properties of the design. And then, depending upon what algorithm verification tool uses, those equations are computed. If the design space is huge, which typically is the case, then doing it over multiple cycles, for example, let's say the number of possible state space can explode. And sometimes even the equations after for multiple cycles may not even fit the memory of even most big machines that we have today. So formal verification at a high level, if I want to talk about, runs into complexity. And this complexity is of in terms of solving equations. If the design space is very, very big, able to solve all these equations, become these equations can become very, very huge, and it becomes very difficult to solve these equations. So even formal verification comes with its own challenges. The one of the major challenges is complexity in all these equations which comes into the picture. There are ways, of course, to resolve this complexity, but that is what we are going to talk about, and how in the context of how formal verification is being adopted. So basically, think of this, right? Think of this as an as you grow in the state space, your complexity or the number of factors in your equation is a lot, and this is where formal verification becomes challenging. The language of the formal verification is not very different from what we had seen when we had done the basic Boolean algebra. It uses the same set of basic algebra to solve the equations. Of course, it does it over a big design space. But these equations are similar to what we had run in basic Boolean algebra, commutative laws, associative laws, your De Morgan's laws. Those are the equations it uses. But of course, tool does that automatically rather than doing that on the paper. Also, one of the terms you will use for which is you will very commonly hear for formal verification is BDDs. BDDs are basically binary decision diagrams, where which are basically graphical way of writing certain equations in the design. Of course, you don't have to, as a user, you don't have to get into those details, but it's important so that you are aware of what these things means. For example, let's say a mux in binary diagram can be written like, okay, when x is 0 takes z, and when x is 1 it takes y, and of course when z is 0 it takes 0 or 1. So basically a mux in a simple binary diagram can be written something like this. So this is a mux, sorry, so this is a mux, and let's say x is at the select line, and this is z, this is y. So when x is 0, whatever is the value on z, if z is 0, then 0 is taken. If z is 1, then 1 is taken. But if x is 1, y is taken, and similarly. So a mux basically can be written as a binary decision diagram, something like this. When x is there, x is 0, it takes z, otherwise y, and if y is 0, value is 0 here or 1 here. And of course, if z is 0, well, output is 0 or output 1. So typically, designs are converted into these sorts of graphs, which are known as BDDs or binary decision diagrams. And these are converted into these graphs because then computer scientists or engineers who write these tools know a lot of graph traversal, know how to solve problems related to graphs. So in that way, whatever the digital design is, if they're written in form of these BDDs, we can use computer science algorithms, which are also used in other applications. For example, let's say maps, Google Maps, right? Similar set of applications or advancements which are done in technology can be used here. So your designs are converted into some sort of these binary decision diagrams, and then those can be used to solve equations or verify your design formally. Because a small case of a mux, similarly, other kind of gates can also be written, then multiple operations. With the operations we talked about, these and operations or operations, going for flop also these diagrams can be created, and then these equations can be solved. So thinking of it at a high level, if you're not a tool developer, basically your design can be converted into equations, and these equations are represented in these sort of graphs. Now, one common language which we talked, right? In order to leverage the power of formal verification or to prove correctness of your design, first, somehow you have to write what is the correct behavior or what you are expecting from the design. And that most popular way to do this is through properties. What are the properties of your design? And we talked about simple properties. Like, for example, counter always increases by a value 1 at every clock cycle. That's a property of your design. These property are written in a language. These are behaviors of your design. Something written, something called as assertions using system verilog assertion language. So you have tools and technology which convert your RTL or your design into Boolean equations and BDDs that we talked about. So that becomes your design, what you have implemented. In addition to that, you write SVAs, system verilog assertion, which is kind of your expected behavior of the design. So you have SVAs, SVAs, which is expected behavior of your design. And then you have RTL, which then is converted into what is known as BDDs or binary decision diagram. These two are matched against one another. Okay, so somehow using tools and technology, mathematically it's proving, okay, this is your expected behavior of the design. And this is what you have created RTL, which is converted into these binary diagrams. And then these, whatever, based upon these binary decision diagrams, whatever the expected behavior is that matching or not? Compare this to simulation. What you are doing was your expected behavior, you will kind of convert it into a monitor, and you're giving some inputs to DUT, and whatever outputs were there, you are computing. So you're writing test bench for each particular behavior you wanted to verify. Here you're not writing test bench for each particular behavior you wanted to verify, but you're writing your behavior or how your design is supposed to behave in some sort of assertions. And your design is not being simulated like here, where you basically at every cycle it was simulated. Your design is converted into some sort of equations, and then you are mathematically verifying it. So this is the basically difference between your simulation and formal verification. So what kind of assertions can you write? Assertions are behavior of your design or properties of your design. So assertion is a statement about your design that you expect to be true. For example, a very simple assertion which is basically done is, maybe there is a property or a fact in the design. You basically never expect a grant to agent 0 when it was not requested. So basically a grant was not you cannot give a grant when it was not requested. So basically when it is not requested, you expect this to not turn 1. So when request is 0, that means not of request, you grant cannot be 1. So basically this, without going into syntactical details, which you can check in our course on system verilog, but basically you assertion is a property of your design, and you're writing this property. Okay, when request is not given, when request is 0, your grant cannot be 1. You cannot get a grant when request is 0. So this is a behavior of your design, this is a property of your design, and you can write this in system verilog syntax as assert property. That means assert this is always true, this is property of my design is always true, and then formal verification will read this and try to verify this mathematically. In sometimes what happens is assertions are not good enough. Okay, sometimes you can only verify, or whatever your RTL you have given, which is then converted into BDDs, you cannot verify without some assumptions in the design. For example, there can be, let's say, some configuration registers in the design. Okay, that you're using design in a particular manner, and let's say those registers are all, let's say, will have value, let's say 0 1 2. Okay, let's say these three register has value 0 0 1. Only then this property is true. Okay, so for that, it can only be verified. Your design can only be verified then when these registers are programmed this way. So those assumptions or those things which are pre-required before you can verify your design are known as assumptions. So system verilog also provides a way to say assume something in the design. Now what will happen is when your formal verification is verifying this kind of becomes an assumption for formal verification, which is basically formal verification will assume, okay, it will say, okay, now if I am assuming this is true, can I verify this property? So system verilog provides two important aspects. One is assumption, one is assert. Assert is something which you want to verify. Assume is something which you should assume to verify it. For example, let's say as we had done in mathematically or in our Boolean algebra, let's say we want to prove some identity, let's say x plus y equal to z. But assumption is, let's say, x less than equal to y. Only then you prove this. So this you will kind of write as an assumption, and then using this assumption, your tool or technology will verify whether this equation is true or not. Okay. Okay. Then cover points are points basically which you want to say occasionally true and whether I have verified it or not. So I'm not going into a lot of syntactical details. I'm covering this at a high level, but you can have cover points which are always sometimes true, and you want to check whether that happened in your design or not. So basically, formal property verification is you will give your design, which is RTL, which will convert into binary decision diagram. Then you will give a certain set of assumptions to your design. Like we said, okay, these configuration registers can only be programmed to this value. And then you will say, give some assertions or cover points which you actually want to target or verify. So you'll give some assumptions, you will give your RTL for the design, give some assertions, properties which you want to check. Then formal property verification will take all of these input. Then it will say, okay, these are the properties I have proven. These are mathematically proven. But and these are the properties where I have proven you said this is always going to be true. Let's say you said counter is always going to increase by one, but I have found a scenario or a corner case where counter is not going to increase by one, and that will be your counter example. So it will be a failure of your property. If it was able to prove for everything, it will say, okay, this property passed. That means it's a true statement for your design, mathematically proven. Or if it finds cases where it does not was basically failing, it will say, okay, these are the counter examples for your design where it was not able to, it actually was proven that your equation is incorrect. But formal verification will also have a certain kind of category which is known as bounded or inconclusive proof. If your design is very big or complex, maybe it was not able to prove. Maybe the equation proving becomes so difficult or complex because of so many states in the design, it was not able to prove for certain aspects of the design. So in when you're writing test bench or doing simulation, you only have two cases, whether the test bench passed or whether the test bench failed. It never has, okay, it was inconclusive. But when you're running formal verification, your results will fall into one of these regions. Property verification, it proved something, it failed on something, or it was not able to do a conclusive proof. And that is why ideally it should be able to do this, but because of the complexity, it will also fall in this range. And that's the limitation of formal verification. So basically, ideally, formal verification, let's say this is all the possible states, all the design space it wanted it to cover, but maybe it was able to cover only this particular set of state, and some it did not cover because you said, okay, assume this to be true, so some areas it will not cover, but typically it will also cover all this possible space, but some possible space it will also not be able to cover because of the complexity of the design. So then a natural question is, if it is still not have 100% of the coverage, how does it help? How does it help is in this area where it is able to cover, it is covering 100%. So in a specified area, in a specific area, it is covering 100%. Your simulation, even in the specific area, will never be able to cover 100%. So that's the advantage it provides. So even though there are uncovered areas because of formal verification, but whatever area it is covering, it will cover almost 100%, and that's the advantage it provides, which test bench or simulation based will not be able to cover. So let's say take a some simple example, right? You would have seen like a combinational lock. You set a number, and only when that number is pressed, it gets unlocked. So what can be the kind of properties for this, right? As in you will have some digit which will you entering the design, you will have some clocks, so the resets for that design. That number which you are given converts to binary, and then basically checks whether it matches the number which has been stored. And if it is stored, then it will unlock or open the door, for example, right? Okay. So basically, what will be the properties or verification goals in the design? You want to check when the correct combination is given, which basically first number is correct, second number is correct, third number is correct, the door opens. And these are some constants or some values which you have initialized. Now that is one goal. Like when correct, you give correct number, it opens. And what will be no incorrect number can open the lock. So what are the properties for your design? Okay, what are the properties for your design is when first part is correct, second part is correct, third part is correct, then open the lock. So that's a property for your design, that if these three numbers are, let's say 174, 1, 7 and 4, then input is good and door should open. That's one of the properties of the design. What will be the other properties of the design? Okay, we'll have basically, without going into syntax, if current plus last two codes are not matching, then it should not open. So these are the only two properties on your design, and you can imagine, right, that there are only two properties in the design. But in order to do test bench, let's say you want to verify this test bench, there are 9 possible combinations on first number, 10 possible combinations on second number, and 10 possible combinations on third number. You'll have to write at least 10 into 10 into 10, right? At least 1,000 test cases. But formal verification, you just have to write a few properties, and that will be able to verify in your design. So that's the power of formal verification. So basically, now formal verification typically will come out with the results. Okay, for when it's opening, it's able to pass that it only opens when this combination is given. For some cases, it will say, okay, I have checked till one cycle, checked four cycle. That is, we are bounded. I'm not completely proven, but for certain set of cycles, I have proven. So this is kind of formal verification results you will have. But think from this example, you are able to cover a large set of cases by just writing a few properties, right? The simulation always runs on specific test vectors. You give a certain set of values, and then only those values are verified. A formal verification analyzes all the possible simulations as limited by assumptions. So it is able to do much more complex tasks, plus or able to do much more coverage and verify a certain parts of the design. If it finds, okay, there are certain parts of the design it actually failed, it will also usually provide a counter example. Okay. So basically, right, formal verification, you give an assertion or a property which you want to verify. You give an assumption which will be used an assumption, and a cover point, you will check whether a particular point was covered. But two important aspects of formal verification are assertions and assumptions in system Verilog language. Assumption is something which is assumed, that will say, okay, this is true. Only then I'll verify. Assertion is something, the properties it's going to verify on your design. Okay. Now, what happened was, this is how, so initially you had like that Intel bug, formal verification came into the picture, people started doing formal verification, languages were developed to write properties for your design, and those properties were verified and this came to be known as property verification or formal property verification, FPV in short term, formal property verification. If you have any questions, please feel free to type it in the chat window. I've also shared a form link in the chat window. If you fill that form, you'll get a certificate for this webinar. Now, we started with the, so if you have any questions, please type it in the chat window. So we then went basically came into property verification. So we started with formal verification. Formal verification took the shape of property checking, property verification.
Nothing.
And then let's see a certain set of transformation which happened from property verification to something known as formal verification apps. So what the challenges with property verification were, the idea of writing a property is very good. It's very simple to write a property, but practically adding effective assertions is not so simple. It requires a lot of thinking. It requires a lot of work to find all the properties of your design and write that. And it required a very huge set of investment to write all these properties for your design. Okay. So that was one challenge of the property verification. And second challenge for the property verification was the completeness challenge. Completeness is very, very expensive. As, as your design sizes increases, the complexity of solving these formal equation becomes increases exponentially. So if the state space is huge, your algorithms may not converge and tool can just endlessly run or come out with a lot of bounded, time limited, inconclusive proof. There are a lot of techniques to handle this, but those techniques are very high touch method. And those can only be used by people who have been in formal verification and are formal verification experts. So basically, with property based formal verification, what happened was, in order to successfully use it, you actually needed very specialized formal verification engineers so that they can use all these techniques to reduce the complexity of the formal. And basically because of that, it did not reach a level which was not possible to widely deploy this formal verification technology. Even though it has a lot of advantages, the completeness was a challenge, and that solving that completeness required formal verification experts. And since you can only have so many formal verification expert, this basically what we formal verification, property based formal verification was not being able to deploy it a lot. So how this was the challenge which people run into. Then what what evolved was formal verification apps. What are formal verification apps? So basically, the problem with property verification was that in order to solve property verification was trying to solve any general mathematical equation, any general property you can write, and formal verification engine will try to solve that problem or prove that mathematically. What people realized was, we have had an example of, let's say, formal equivalence checking. Okay, formal equivalence checking works very well, right? As in any almost every engineers in the world uses, whoever does synthesis uses formal verification equivalence checking. So it's widely deployable. It does not, like, unlike property verification which you're trying to solve general problem, formal equivalence checking which is solving a particular problem targeted a particular application, it is scalable. Every engineer is able to use it. You don't specifically need a really good formal verification expert to solve this. So this gave an intuition that target maybe specifically targeted formal verification solutions, specifically target to specific application, was the way to go. And basically, a lot of companies which came up like Jasper, now even Synopsys formal verification moved to, they still support property verification, but now they basically also entered into doing a lot of formal verification apps. And these apps, basically, you don't need really specialized formal verification expert to solve it. These are bundled in such a way that similar to formal equivalence checking for a specific problem area, it works really well with a little or minimal expert effort. So that's how it basically formal verification app came out. Apps work on the principle that for a particular application, a similar heuristic, similar kind of techniques can be applied, and these techniques can be applied automatically by the tool. You don't have to, tool can be finely tuned, automated to do this. So there are a lot of formal verification apps come in, functional safety related, equivalence checking related, low power related, auto checks, which we'll talk about. So the basically if you wanted to do formal verification, there is an app which can help you do that particular kind of application. So this is how formal verification has evolved today. Starting from property verification. Property verification is still used because it still is adds a lot of value, but then is a lot of wide scale deployment has been formal applications, formal apps. So let me talk about some of the apps which exist in formal verification. The image source for these is from Synopsys, but there are multiple tools which support these apps. Like for one of the example of is auto checks. Different vendors have different names for these kind of checks. Basically it looks at RTL or a module and automatically generates assertions or checks for that particular design. For example, some examples of check may be FSM deadlocks, overflow. A lot of this can be done automatically, formally verified. FSM deadlocks is a great example of that. Is tools will read your RTL, and just based upon those RTLs, verify a certain set of checks in your design. So this is one of the apps which is very commonly used, and this then avoids writing test benches for those checks. You don't have to write test benches for those checks. Another area where it is used is X verification. Like so it will inject S at certain logic in the design and verify your X is basically observed in the design or not. Formal coverage analyzer, it can analyze unreachable part in your RTL code. It can, these unreachable code can be there because of legacy code or unused feature. This then helps you identify, okay, so typically, right, because unreachable part of the code, maybe it's under an else statement which is never going to be executed, maybe it was created earlier, no longer being used, but you don't want to change your RTL because you don't know, right? As in you don't change unless there is an issue with your RTL. So then basically, but formal verification coverage analyzer can analyze those part of the design, point it out to you, and then you can use that information to improve your coverage, exclude those areas from your coverage analysis. Connectivity checking is basically the designs are very complex. How do you verify top level connectivity? What pin should be connected to what, under what conditions? IO connectivity is the prime examples of that, which has complex configuration. So how do you ensure all cases are covered? Of course, in order to cover these thousands of cases using test bench can be cumbersome. And also, this does not require doing deep formal sequential verification. You can only do maybe limited formal verification. So you'll always come back with the result. The chances of getting unbounded or inconclusive results are lesser. So connectivity applications were developed, and it's also now available in a lot of tools and vendors. Then sequential equivalence. So we talked about combinational equivalence. Some design when changing from RTL to gate will insert clock gating logic or power gating logic. This requires slightly advanced version of doing equivalence checking, which is known as sequential equivalence. So there's another targeted app which was developed and can do verification. So basically, as you can see, right, property verification has its own place, but a lot of new apps which does not require really a super formal expert to do verification have been developed, and this is how formal is very widely used in designs today. You have register verification. Your CPU designs have thousands of registers. This logic is very complex. Some can be read-only registers, some can be read-write registers. There can be registers which are cleared on read. This again, for register verification, formal app will automate checking of these registers against IP exact or similar specification. Security verification. Security is a very big challenge today. You can have data leakage, which means secured logic data can transfer into unsecured logic, or data integrity non-secured logic to secure logic. This is another evolving problem space area, and there are apps for formal verification doing this security verification as well. Then data path verification, again with your AI hardware, GPUs, a lot of mathematical functions. So data path function like plus, minus, multiply, divide is very commonly used. And data path validation is a challenge. It requires, because it not only, it can basically increase exponential in numbers. Again, a new technology or app which was developed, it was basically done on the same principle as equivalence checking, where you can prove that your C model, which for a lot of these cases our C model can be done, is equal to your RTL or not. A formal verification app was developed for that. So data path validation can also be done with formal verification. So because of all these technologies, all these apps which were developed, you have adoption of formal verification now increasing. Formal verification, property verification also has its own value, and even that adoption is increasing. But in addition to that, automatic formal verification adoption also increasing because of this. Now, looking forward, as in if you're an engineer or if you are a college student, what is the scope of formal verification? What is the future scope of formal verification? As I said, right, there are a lot of companies. Intel is a prime example of that. They really focus a lot on formal verification. There are a lot of EDA companies, of course, they need a lot of application engineers for formal verification. And of course, there are a lot of services company which primarily does service purely based upon formal verification. There is a company which I know recently called Oski, which was basically used to provide formal verification consulting, and actually now acquired by NVIDIA. So basically, there is a lot of scope in formal verification. There is a lot of scope in verification in general, and if you know formal verification, you can actually become very, very sellable engineers. So looking forward, a lot of new kind of hardware complexity in the hardware is increasing. So formal verification definitely will be needed. So more and more security verification will be needed. There is, because of AI hardware, improvement in your data path usage. So even that is verified formally. There'll be extension done basically to formal methods specification. In addition to that, there are new technology which are going to be used for writing assertions. Automatically specs can be converted to assertions. There's cloud-based formal verification which is coming up, machine learning based technologies which are also coming up, or also there are complex multi-core architectures which are being developed, right? Chiplet based architectures. So these designs are going to be huge. How do you verify those designs? Can formal verification be used in those areas? That's another hot area for research. So looking forward, I see a lot of formal verification, lot more apps to be developed. Security verification I see is very, very active area right now, and chiplet is very active area right now. So this is how formal verification continues, will be used, and there will be a lot of scope of that. Let me look at, so this covers our slide. Someone had a question whether the slides will be shared. We will be putting this video on YouTube. So you'll be, you can anytime come and look at our YouTube video. In addition to that, we'll be also be launching a formal verification boot camp. So if you follow our LinkedIn page on VLSI Deep Dive, I'll just search for VLSI Deep Dive on LinkedIn. We'll be having a formal verification boot camp soon. So if you're interested in learning formal verification, learning thoroughly, we'll have a 3 to 4 week boot camp where we'll be basically help you write formal verification. Yes, we'll be using formal verification tools for this application. Okay, so I'm posting. So basically, there is If you want certificate for this webinar, I'm posting this link again, and then I'll go over the questions which have been asked by people. So let me start from the beginning. What is the future scope for formal verification or for a beginner design verification? Should be preferred a formal verification? If you are a beginner, first you start with normal test bench or dynamic based verification and also learn formal verification. If you know formal verification, you'll be more sellable as an engineer. Formal verification is a dynamic verification or not? That is a question. No, formal verification is slightly different. Dynamic verification is more about test bench based verification. Formal verification is mathematical verification. They're not the same. What is the difference between functional and formal verification? Functional verification is basically verifying your design functionally. Okay. Typically, functional verification term is interchangeably used with dynamic verification or test bench based verification. And formal verification is mathematical verification. There's another question. What is the future scope in formal verification? Uh, I already talked about that. Is there also a scope for physical design? Yeah, of course, there is. As in, all the semiconductor areas are hot right now. Of course, verification is very, very hot. DFT is also hot. Physical design is also hot. So any area of which of your liking, if you choose, that's good for you. So there's another question. Is security verification used only regarding the access of secure data? As in, security verification is primarily focused on data, but it's a evolving area, so there are a lot of other applications which will also come up. There is a question: how can we verify written assertions? Are any free online simulators are there? As in, if you want to verify the assertions, you mean using test bench. Of course, you can verify. There is EDA playground. I think there is Verilator. If you formally want to verify something, there are also free online formal verification tool. I think there is one from YOSYS, YOSYS. Search for that. There is a free formal verification tool also from YOSYS there. The only limitation in that is basically in their opens or free version, they only support immediate or concurrent assertions, which you can learn more about. Sir, is there a question? Is there a scope of field related to integration of VLSI and quantum computing? In my opinion, quantum computing still is in a research area. So please, as in that's my opinion. There is a question: what will be covered in formal verification bootcamp? Will be creating the plan for formal verification. So follow our page, LinkedIn page, VLSI deep dive, and you will get a detailed. Once we post it, you will get a detailed plan of what we'll cover and how we'll cover in formal verification. So there is a question: does formal verification work along with UVM based test benches? Yes, of course. As a formal verification does not replace the test bench or UVM based verification completely. It complements it. So all the verification methods have to be used together to reach 100% coverage. So it does not replace, it complements it. I hope I answered that question. There is a question: bootcamp is chargeable? Yes, there will be a fees for bootcamp. We'll have special discount and early bird discount. So keep an eye for on our LinkedIn page so that you can get discounts or early bird prices. How is the current market scenario for VLSI design and verification field in Bangalore? So one of the challenge right now, we are going through a downturn. So if you are a fresh engineer, the market is right now a little bit difficult, but there is a great scope. As in, if you are able to enter the field, please, as in, try to find an internship, whether it's paid or unpaid, and enter the field, because it's gonna grow very, as everyone is saying, it's gonna grow at a very fast pace, not only in India or also globally, and learn technologies like formal verification, as it is very, very hot. DFT is also a very hot field of area. What is the future scope of semiconductor industry in next 10 engineers? Will it be a boom also? So of course, in next 10 engineers, there is very good prospect for semiconductor industry. Another question is, can IT engineers having 4 to 5 years of experience switch to semiconductor industry? You can switch to semiconductor industry, if you, even if you are an IT engineer. What I would recommend is join one of the finishing school, which typically will have 5 to 6 months of program. You can continue doing that program while you are doing the job. And let's say if you are really highly paid in IT engineers, expect to take a pay cut if you want to make a switch. But overall, you will get a lot of benefits. Can you give an example of data path formal verification? Which one is used, BDD or SAT solver? We'll cover this in more on bootcamp, as in this will be too detailed discussion to do in this general webinar. The person complete PhD and 15 years of teaching experience. Any opportunity in VLSI industry? As in, if, as I said, right, and there are a lot of opportunities. You have to see what matches your skill. What is your opinion on this recession? When is it going to end? As in, we are all hoping early next year it should end, but let's wait and see. As in, that's what everyone is expecting. Is it possible to verify AI/ML based algorithm using formal? As in, a lot of AI/ML based algorithm use data path, which is multiply. So yeah, as in there are parts of those you can verify using formal. I think I've covered all the questions. I've shared the form. We'll be posting this video on YouTube. So if you like and subscribe our YouTube channel, you'll get this. In addition to formal verification, we have multiple other workshops and boot camps which are coming up. If you're a fresher or a second or third year in college, we have Verilog workshop which is coming up. We have timing constraint workshop which is coming up. We have low power verification workshop which is coming up. Then we have STN Tickle boot camps which are coming up. We are also launching an RTL design and a RISC-V boot camp. So do follow our LinkedIn page. There'll be information which will be done. Okay, there is a question why these service-based companies receive very less projects. This is because of because of recession right now. Okay. So thank you, everyone. I hope if you have filled the form, you'll get a certificate. Sorry, on your email. And if you, as we'll be posting this video on YouTube. Do follow our LinkedIn page and YouTube channel for next set of workshops and boot camps which are coming in. Thanks a lot, everyone, for joining.